Chapter 3, Section 5. Slope. Slope is a rate. It's a special rate we can use to effectively graph linear equations. That's mostly what we're going to use it for in this class, but slope's used in real world stuff. In fact, that's where the word slope, when we talk about going up a slope, when we're referring to a hill or something, that's where the word comes from. Is from this geometric relationship between two numbers. And its rate, I'll kind of give away the whole section here as an introduction, but it is a fraction, which means the amount of rise that occurs between one point to the next point over the amount of run or horizontal change. So vertical change over horizontal change. And we're going to get into relationships and what that means with ordered pairs and a lot of things as we go through. Now what they do in most sections is let's relate it to something that we've already covered or some other pieces of information or data, and we can talk about that. And first they start with this idea of rate and slope, and this data that they're giving us here is a comparison. It's a nice model to look at to find out, to make some decisions about when they should replace employee laptop computers. And he says they currently replace them every 2 years. For the new program, he's considered changing the policy, replacing them every 3 years with a more durable model, which I would assume would be a more expensive model. Now the following tables list the costs of replacing computers using both programs. And the two-year replacement is here. Years since the start of the program, well, at the very beginning there's no cost, there's no time that's passed, right? And we're just talking about replacement. They probably, year zero, they had to buy a lot of things. But in this model, they're just looking at the cost of replacement. So after 2 years, they're going to have to pay $3,000 for a computer. And after another 2 years, it'll be $6,000, the cost of the computers. In other words, $3,000, so it's adding on here as we go. 6 years, $9,000, so on. If I did a 3-year replacement, and I'm going to buy a computer that costs $4,000, so at the end of 3 years I buy $4,000 worth of computers. I would hope, a little more timely, these computers don't cost this much anymore. But here's the data and see how that works. And you could look at this and start comparing something. At 3 years, I end up spending more money. In this model, at 3 years, I still only spent $3,000. But at 4 years, I end up spending $6,000. But in this model, at 4 years, I still only spent $4,000. 5 years, $4,000, and so on. But you're going to see some things where there's a comparison of time, and we can see some things that are going on. Okay. Well, we could continue looking chart to chart and doing that, but this is good data to graph. And if I graph this stuff, I can look at it, and it kind of gives the image that I could project. So here's all the same information. I got to make sure my axes are labeled right, where this is number of years since the start of the program and cost of computers in thousands of dollars. So they do some things here. Make sure you explain that so you don't have to write out 6,000 here. They just say 6 for the number of thousands. And here's the ordered pairs. Remember, the first number is a horizontal change, second number is vertical change, so on. So here's a graph of both of those things. And if I want to find a rate, really, the rate of change that's happening on here, it says in the 2-year deal, I spend $3,000 every 2 years, or $3,000 per 2 years. It sounds like a rate, doesn't it? Or 3 over 2, $1,000 per year, or $1,500 per 1 year. Okay, a lot of ways to say that thing. In a 3-year plan, I get $4,000 every um, 3 years. So I ended up with $4,000 per 3 years, or 4/3 $1,000 per year, or $1,333.33, or really 3 repeating because we have thirds per year. Now I can make a comparison. If I'm going to say, well, I'm still trying to make a decision here. In this case, I end up spending 4/3, every year, 4/3 of $1,000. And here I spend, on average, 3/2 per year. Okay, so it looks like on a per year basis, this is probably going to save some money. There are other factors there too, and a lot of assumptions about what the price of computers will be in 2 years or 3 years too, and what new operating system somebody like Microsoft might come out with that really makes hardware obsolete faster, right? So there's a lot of variables. But that's a way to compare and look at rates and those kinds of things. And really what they're doing here, I could push this back right into the graph, this 3/2. If I look at this, if I talk about slope again, where it's rise over run, this means I'm going to go up 3 and to the right 2, and that's going to get me to the next place on my line. And that's what it does here. So if it may not equate to the actual ordered pairs, but if I start at this point and I go up 1, 2, 3, which is a rise of 3, and to the right, which is a positive 2 or run, I end up at my next point. Okay? And so on. I can go from here to here. I go up 3 to the right 2, up 3 to the right 2. Looks like I could go up 3 into the right 2. I'd end up at 12 or 10, 15, right? Well, the rate that they're talking about here is 4/3. If I went from this point to this point, what happens with my rise over run? I go up 4 and to the right 3, there I am on that next point. And that's what they're going to talk about in that relationship with slope. So I took that idea of, hey, these are really rates, and I'm just correlating it with slopes sooner than they are, right? Well, example 1, they talk about that, and here is a picture of that deal. Nice picture of just what I just did, right? They say, here's an ordered pair, 4, 6. How do I get to the next one? Well, I could go up. There's really like a map to it. A rate of change, or a slope, we're going to call it, is if I started at 0 to get to this point, I would go up 6 and to the right 4. And why I'm saying it in that order, because we're used to doing it the other way. I could have also gone this way. I could have went to the right 4 and up 6, right? They're starting to set up this idea of vertical change over horizontal change. So they do the vertical thing first. That's my numerator and my fraction, and the horizontal change second in this case. So I get 6/4, which simplifies to be 3/2. And that's what they're showing. Notice that anywhere you go in here, I could actually go from here and go up 3 and to the right 2, and hey, I'm at another data point in this graph of this information. So they're still talking about that same example. So using the graph of the 3-year replacement program to find cost of computers per year, we could make some decisions, and it's based on those comparisons and rates and slopes, right? We're going to get to. Also, we can note that if I take ordered pairs, I can find out just from the ordered pairs. I could put them on a graph, but this gets difficult if the ordered pairs are not whole numbers, right? Or integers, or they could be fractions and decimals and all those kinds of things that You could draw a picture of it, probably be pretty close on your graph, but you're not going to really know what change happened unless it falls right on the grid lines. And they tend to give you those kinds of things so you can see more easily what's going on. So the ratio, or basically a vertical change in y, to the horizontal change in x, rise over run, we're going to call that slope. Well, I could find that out right from the ordered pairs. And I can do that by taking differences. If I think about from this point right here, and if I was going to say, what's looking at this ordered pair and this ordered pair, can I figure out how much rise occurred? Well, the second number indicates the rise, right? The vertical change is 5 here, and the vertical change is 3 here. Well, if I went up 5 and this other one went up 3, what's the difference? I take the subtraction of that, 5 minus 3, and that'll give me 2. And that would be the same as going like, hey, I got to go up 2 and then to the right a certain amount. Well, the same thing with my horizontal parts, or my x coordinates, which in this case the x-axis. The first number is my horizontal change. Well, here I got 2, I moved 2 to the right, and this one I moved 6 to the right. So what's the difference between that? Is 4. So we take those differences, and we have to be careful because subtraction is not commutative. I have to make sure if I take this vertical distance minus this vertical distance, this vertical change number, this vertical change number, I got to make sure I do it in the same order with my horizontal change numbers, my x coordinates. So you have to be careful. One of the reasons I don't like subtraction, but in this case we need to look at the differences to get that change that occurs. And that's how they say we have vertical change and horizontal change. In other words, if we simplify that fraction, we end up with 1 over 2, which means if I want to go to the next point on my line in this case, I could go up 1 and to the right 2. And look at there, you'd be right on that line again. Though, even though you don't have an ordered pair there, I could figure that out. To go up 1 more, I know my y coordinate is going to be 4, and I'm going to go to the right 2 more, which is going to be 4, 4. Right there, and that's, if I look at the graph, that looks like what it is. And just by working with that, you need to practice that, I can determine what the next ordered pairs are, hopefully without having to draw the graph and doing that. This is basically, they're going through this and they're saying, this is so important and this is so useful, we're going to name this a special name, and it's called slope. And here's the definition of that. Now, all that visual, all this talk about, what's really going on with ordered pairs, here it is in an algebraic definition. Now, what they do here, which you probably haven't seen yet, is they put these little numbers beside the variables. And the only reason that they do this, because order is important. I got to make sure I know if I'm talking about point 1 or point 2. In other words, this x sub 1 is how you say that, and y sub 1 is really talking about point 1 right here. The x sub 2 and x sub y indicate that these numbers are from the point 2. So when I look for slope, which we use this m for slope a lot, it's the change in y, or the rise, and I can determine that by taking the y coordinate, or the vertical movement number, right, of the ordered pair, and we take y2 in this case, and subtract the y coordinate from the other point, which indicates vertical change, right? So what we're doing is getting the differences of the vertical change between these 2 points, or we're looking at this blue line. And I can get that by taking y sub 2 minus y sub 1. That's this equation. Well, I need to get the run, the change in x, the horizontal change, run, right? A lot of words for that. Well, I need to make sure I do the subtraction from the 0.2 because that's what I did for the other one. So I have to take this minus that. This will give me these change in y, or the rise. This will give me the run, or change in x. So if I have two ordered pairs, I can find out what the slope of the line that goes through those 2 points must be. And with this information, again, we're going to do a few things. One is we can actually use this to eventually to write an equation for this line that goes through these 2 points. But right now they're just saying, well, let's look at how do I determine what the slope of the line is. What's the rise over run for this line that goes through these two ordered pairs, -4, 3 and 2, -6. Well, the solution is to use this algebraic expression or definition of slope. So they take that, they determine which is your 0.1 and 0.2. We need to know that slope is change in y over change in x, or slope, another way to say it is rise over run. I'll say that a lot. And then they determine, say, hey, let's call this 0.2 because it's the second ordered pair they gave us. And I'm going to say this is y sub 2. So I put -6 minus 3. And then I need to do the x coordinates the same way. So I go 2 from this 0.2 right here minus -4. Now, if I do it the other way, I'll end up with exactly the same slope as long as I follow the order. I could say this is 0.2 and this is 0.1. You'll get the same slope. Well, when you do the math on this, make sure, remember, subtracting negatives or negatives with subtraction are troublesome, right? You end up with a lot of errors. I would go -6 plus -3, which is -9. 2 minus -4 is 2 plus 4, 6. Okay. Well, then I simplify this fraction by, this is really 3 times 3 over 2 times 3, which I have a negative. I could know I'm going to have a negative in there. I could put the negative and then just deal with the fraction, which is 3 over 3 times 3 over 2, which means it simplifies to a -3/2. Now what does that mean again? Now I'm going to go back to what did I just come out with? It says that there's a -3/2 slope, which means I could go -3 over +2, which means I could go from this point, if I chose this point, well, -3 over +2 would mean I'd go down 3, which would put me right on the x-axis, and to the right 2, hey, I hit another point on this line. I could go down 3 to the right 2, I get another point, down 3 to the right 2. It's just like walking this right triangle to another place on the hypotenuse of that triangle, just to tie in some geometry. Okay? So that's slope, and this is called the slope formula, is we can always find slope if we have two ordered pairs that are on this line that we're looking for. And it makes no difference, this is which point is considered x sub 1 and y sub 1, and I kind of walk through that. What's important, because it is a subtraction, is that if you say 1 is 0.2, and you got to make sure you use it as 0.2 for both your x and y values, okay, for your differences. Subtraction is not commutative. Here's a little bit about graphing calculators, which are really handy tools, but we're not using these in this class. Okay. Then they go through this horizontal and vertical line stuff again. We've already done this once, and really what they're going to say is, let's look at slope. What happens with horizontal lines and vertical lines? Now, I can go right back to it. I can take ordered pairs like this, like they do, and use the slope formula. And they say, well, I got -3, 4, and 2, 4. Well, they use, this is 0.2, the -3, 4. So they take the y coordinates, 4 minus 4 over negative 3 minus 2, right there. And they end up with 0 over negative 5, which is 0. So it looks like, and if you think about that, again, this vertical line stuff, we talk about this a lot. What is true about every ordered pair on this horizontal line? In this case, every y coordinate, excuse me, is 4. It has to be on this line. So if I take the difference of the y coordinates on any points, I'm going to end up with 0. And then the number that I get on the bottom, it will change a lot. If I went from some point here to some point here, I'm going to get a larger number or larger difference there, either positive or negative. But I still end up with 0 over that number, which is 0. So what they want you to do is recognize that horizontal lines have a slope of 0. And that's why they box that and put that in. Now let's look at example 4, which is a vertical line. Now rise over run, again, is slope. Well, if I take these 2 points, what is the rise? Well, I go from 4 to negative 2, that's 6, right? And if I went from there, there's a negative 6. I went down 6. I can actually do that graphically without having to go 4 minus negative 2, which is, in this case, would be positive 6, right? And so on. But when I look at my run, what's the same? Every ordered pair on this vertical line is going to be negative 3. And the difference of my x-coordinate is always going to be 0. Just like when we were talking about intercepts, I said, what's really true about every point on the y-axis? Well, the x-coordinate is 0. It's the same number. Well, on any vertical line, the x-coordinate is always the same number. So in other words, I'm going to get a denominator equal to 0, and that's undefined. We cannot divide by 0. Try that on your calculator. Put negative 6 divided by 0, and you're going to have something that says error, depending on the type of calculator what it says, but it's going to indicate there's no real value for that. So the only thing we can do in this case is to say that the slope is undefined, or we say there's no slope. And when I say that, it means I have a vertical line. Now, I can go back to why can't you divide by 0? Remember that division, if you think about what is multiplication, it's multiple adding. Well, division is multiple subtractions, right? We say subtraction is the opposite of addition, and multiplication is the opposite of division, and vice versa. Well, then think about that. Division is really pulling out a certain number over and over out of like a pile of chips or beans, right? If we were talking about that when we were little kids, I don't know if they use beans anymore, and I know they definitely don't use jelly beans because the kids like me would eat those things. But so they do that, but we're taking groups out, and we're doing multiple subtractions. And if I think about that, if I have some number like 12 divided by 0, what I'm saying is how many times can I subtract 0 from 12 to get to 0? And I would do that. I go, well, 12 minus 0 is 12. There's 1, right? 12 minus 0 is 12. Again, there's 2. I could do that forever, for infinity, and I never really make any progress towards this idea of division. So that's what it means. It's really not defined. It doesn't make sense when you have a division by 0. So slope is undefined. And then they get into some applications which are, they're going to talk about slope compared to grade, and which also points out this, to me it seems like we're so scared of fractions that we have to change things into percents, which are really fractions, right? Percent means hundreds, something over 100, which is a fraction. So we end up with grade 2, and they talk about grade of a of a hill or something like that. It is a relationship between rise and run, just like slope, except that they want the run to be 100 feet or 100 miles or 100 something, which is a percent. So when they say we have a 3% grade, that means that I have a rise of 3 something for every 100 of something that I go. So if I want to talk about it in feet, it would be I'd go up 3 feet for every 100 feet I go horizontally. And so, the same idea. If I went with that grade, if that truly was the true grade of that whole thing, if I went 900 feet, and that's what they're talking about in this example, if I went 900 feet horizontally, how many feet would I go vertically? Now that's usually what we don't do that to try to determine the size of a ski hill. Really what we do is we can determine slope, the kind of the average slope of the ski hill by taking the top point and the bottom point, and that difference is the rise here. In this case, they got a nice picture here. There's a 720 foot difference between the top and the bottom. And then horizontally from here to here, which is a little tougher to measure unless it's like you'd have to drill a hole into the hill to get right below that and stuff like that, which is not plausible. But they have instruments that can do that. And so what we have is then a rise of 720 feet over a run of 900 feet. Sounds like slope, doesn't it? Well, when I want to illustrate that in something called grade, is we take that fraction and make it a percent. That's all. In other words, I could represent that as some number over 100. That's what percent means. So I could take 9 and divide it into 720 is what I would do. Especially if I didn't have a calculator, we tend to say, percents, we need calculators. I need to change it into a decimal and then move the decimal, and then hopefully I remember which way do I move my decimal. And some of you will make errors at that. But if I remember that percent just means hundreds, if I get this simplified fraction of 8/10, so I simplify that. Well, if I have 8 over 10, how many out of 100 is that? Well, it'd be 80 over 100 is the same as 8/10, which is percent. 80 hundredths, 80%. Okay. And that's really all we go through, and they kind of throw in this application using grade. And they use grade a lot on mountain roads, so truck drivers, especially if they have a heavy load, they understand what the grade is, or how much rise is going to occur, or how much fall is going to occur, right? The change vertically for how many feet that they go ahead, or miles, or whatever. Because if they're going downhill, if they have a heavy load, they need to make sure they're in the right gear so they don't have to use their brakes too much, because they can burn up their brakes. And you've probably seen those runaway truck ramps, and that's what happens if they get on a highway and they're not in the right speed, or basically gear ratio to maintain a speed that they can make it through their curves. They're going to have to use their brakes a lot. And it's hard when you have that much force being pulled down a hill to actually change gears, so you're kind of stuck in the gear that you started out with, and thus you end up in situations where the brakes are just all used up by the time they get down, or worst cases, they're used up before they get down. Okay, so pretty good lesson on that. Again, we're going to go through, we're looking at slope. You really got to get firm about what slope means, this rise over run, how we can get that from just two ordered pairs, and then we're going to use that to graph linear equations almost exclusively, and we're going to get to some forms that we can pull out the information very easily and then just graph from that.